So we're starting from notthefuture.com/howtocode/3z this time. Control U, get the source code. Polygon drawing is better, but it's still wrong, as you can see, so let's go do Newell's algorithm. Wikipedia lists how this works, but there's kind of still a lot to think about in terms of implementation. And, trying to Google it, we don't even get like really a great implementation of it on the first page of Google. And implementation is the part that you have to really think about. So I spent quite a bit of time thinking about this, and I came up with my own sort of method, which I don't know if this works yet because I haven't programmed it. Let me go and explain it. Up here we have some polygons, but that's the player. This yellow line is the viewpoint, and this line right here is the screen. The first step is the z-test. So let's look at the top-down view. And we've been sorting our polygons by this point in the center, and then drawing them from the farthest to the closest. But now we're going to sort them by finding the closest edge to us. So first, starting with this polygon over here, we check to see if the max val contains any of the other polygon's min val. I don't know which one is which. Whatever. And if it does, then we're going to compare these two polygons. If this red polygon was all the way out here, we wouldn't have to even compare it against the blue one because it's so far away, right? And same if it was all the way back behind it. But if this red polygon is somewhere within the min and max values of this other polygon, then we have to continue with our checks. So that's the first step, but then we're going to actually go and look at the screen. And so the next thing that we do is an X test, and we check to see if these overlap in their X values. And in this case, they don't. But if they did, they might look something like this. And if they overlapped in our X values, then we'd go and do a Y test. And if they overlap in both the X and Y directions, like in this case right here, then we go on to the more complicated tests, which is like what I have written here. Compute planar equation of polygon I. Find line from each vertex of polygon J to player. Find intersection of line and plane and compute z dist to the point. What the frick am I talking about? Okay, so then at this point, we're going to extend this plane essentially outward, and then we're going to check if all the vertices of this polygon are all on one side of it. So this polygon would essentially get its plane extended, and as long as all the vertices are not are in one direction of it, then we pass our check. And then the fifth check, you do the same thing with the other one, and you check to make sure are all of them behind or in front of the plane. And when I say extend outward, I just mean find the planar equation, which you do by taking the cross product of the vectors. So all this I wrote earlier is not totally useless. And earlier I said this would take too much computation to do, but here we're only doing it on, say, I don't know, there's like hundreds of polygons as opposed to millions of individual pixels. But then if we get past that check, we have to do like a complicated bit. And the complicated bit is a little bit hard to explain, but let me try. So whatever, let's just try to do this. So this doesn't do anything, right? But also, it would be a lot more useful if our polygon was an object rather than an array, because we're going to be referring to a lot of different stuff. So we initialize it with a set of vertices. Okay, so here's a pretty basic constructor. We just go through the vertices, we push them to X and Y positions. And you know what, let's just add dist to mid and fill style. So let's just say var poly equals new polygon. I think we could just pass it QD, dist to mid, ctx.fillStyle. And then just push the poly. Then down here when we render it, we can say var poly equals quads to draw of I. ctx.fillStyle is poly.fillStyle. We sort it based on b.dist to mid minus a.dist to mid. And then the draw quad code looks like this now. If we refresh the page, nothing should change. And yeah, okay, good. Everything works exactly the same. In fact, that makes me suspicious that it's not even using the code. So let's intentionally break it just to see what happens. There we go. See, that looks right. That's the kind of brokenness I want. This isn't even broken enough. And okay, yeah, there we go. Now that's the kind of brokenness I like. Okay, it works. Now some might argue that this should go in its own file and then you should do like a source include, but then when I go and put the source code online, it would be more annoying to just Control A and copy everything, so I'm not doing that. So let's start the process here. So the first thing we're going to need is we're going to have to figure out what the distance to the closest is and the distance to the farthest. We don't use average TZ, so we could just get rid of that. And we just created this to mid in our polygon, but actually we don't need it. So let's get rid of these midpoint finding things, as well as this. So QD is our display points, but let's also pass it the initial quad points as well, and then get rid of dis to mid. And so the difference is QD is what's drawn to the screen, and the quad points are the actual coordinates in 3D space. So go back to poly. I'm going to change this to display vertices and vertices. Do this dot z, and then we're going to have this dot dx for display x, and this dot dy for display y. Get rid of dis to mid, copy this for loop, change this to say display vertices, change the x to dx and dy, and we do want these two dis to mid lines of code as well. So I'm dropping this in here, but instead of using the midpoint and finding the distance to the midpoint, we're instead going to do this dot x, this dot y, this dot z. And it's not the distance to the midpoint, it's just the distance to the point. Let's make another array, this dot distance to, and we'll push to that. But we want a min distance and a max distance. So let's just have the min distance be infinity and the max distance 0. This dot min dist is math dot min of this dot min dist and our new dist to point. We do the same thing for max. Okay, so then that's going to give us our min and max z distances for the polygon. So down here in the render quads function, we no longer have dist to mid, but we do have min dist. So we're going to sort it on min dist now. You have to change these from x to dx because we changed that. Okay, let's see what that does. And we broke it. Why is this surprising? Quad points is not defined. Oh, because I didn't call it quad points, I called it quads points. All right, let's get rid of that. Let's call it quad points. Player point is not defined because we never defined it. Okay. It'll know that XYZ is referring to the global, I think. And so our algorithm is slightly wait a minute, something's wrong here. Okay, yeah, if we look at one of our polygons, only our first dist2 is getting a number. Is that true for all of them? Yeah, I mean, that's happening in the second one, the 16th one. So why is that happening? Oh, I know, because I didn't say this.xi. Right. And, okay, now we have actual values. And, okay, alright, we got it sorting again. But I'm going to do A minus B, so that way they're in the opposite order. And I'm going to duplicate this loop, change it so that this counts downward. So then that's going to draw back to front. Do I have to say -1? Okay, there we go. Okay, so we go and we look at the first poly. And yeah, we're going to make a double nested for loop basically here. but our goal is generally to not traverse every single one of these. We only want to traverse what's in the same z distance as it, essentially. And yeah, okay, to distinguish between the polys, I'm going to call them poly I and poly j. If poly I.maxDist is greater than minDist, then do more checks, essentially. And since they're in sorted order, we know that if we hit this else, the next minDist is going to be greater than the last minDist, so we're going to be done checking. So at that point, we can break out of this inner for loop and then check the next polygon. Are the min and max x values in the same bounds? Are the min and max y value in the same bounds? Okay, so now we're doing the x and y checks, and we want to use the display x and the display y because we're trying to see if these polygons are on the same part of the screen. Because if they're not on the same part of the screen, then they're not going to interfere with each other. We've got to figure out the min and max x values. Since I don't have those yet, let's make them. Let's say poly I dot calc. Okay, I'm going to call them calc extents, right? And also poly j dot calc extents. So here's our polygon object, and within it we can go and we can declare a function in here. We're going to call it calc extents. So this isn't that intense of a process, but I'll do this anyway because this will matter later. And I'm just going to check to see if we've already calced the extents. Right, so we initially set that to false. After we do calc extents, this dot calculated extents is equal to true. Right, but when we start the function, we check it to see if we haven't done that. If we're going to say this dot min dx equals infinity, this dot min max dy equals 0. And then basically we do like the same thing as before here. So min dx, max dx, we find the leftmost point, this dot dxi, and then repeat this for dy. So that gives us the min and max values for the extents, but we only do it if we haven't determined them yet. We have to check to see if they're within the same bounding box. So we say poly I dot max. Is that how you do bounds checking? Hold on. And if that's the case, we continue on with our checks. If they're not in the same region, then we just move on to the next polygon, so we don't have to do anything else. So next is all of this, and this is a lot. Compute planar equation of polygon I, find line from each vertex of polygon j to player, find intersection of line and plane, and compute z-dist to this point, compare against stored z-distance. Ugh, what am I even writing? What does any of that mean? Well, the first thing that we can do is we can find the planar equation of polygon I. We say poly I dot compute plane equation. And let's go make a function for that. Is this how you actually make functions? Oh, okay, no it isn't. You've got to do it like this. Yeah, this dot compute plane equation equals function like that. Okay, yeah, I was making functions wrong, but that's fine. Okay, and now what do I have written down for how to do a plane equation? What is this math? I don't know. All right, let me just copy this. So we just have to take a few points. It doesn't really matter which points, because, if we're doing a quadrilateral, all the points should be on a plane anyway. So yeah, I think what we're doing is we're getting two vectors from the points. We're taking the cross product of those vectors, and that whole thing is giving us this. This is the cross product. And it looks like this. What I should do is I should just make it so that the polygon has an A value, B value, C value, D value. Okay, so vector 1, we do this. Vector 2, we do that. Only difference really is that our indices start at 0. So below that we have the entire cross product written out, but it can also be expressed in this form, and so we're just going to calculate A, B, and C this way. This dot A equals, so that's V1, 1, I think V2, 2, V1, 2, v2, 1. Okay, and there we have A, B, and C written out. It'd be really annoying if my math was not correct. Right, okay, yeah, it's not p1.x, okay, it's this.x 0. And like before, I'm going to say this dot computed plane equals true. And then wrap that. If not, this dot computed plane. Then we run this stuff. That way we don't have to find the coefficients more than once. And then when we actually have some values that we want to test, we just plug it into the formula. So you know what, I think instead of doing this dot compute plane equation, I'm going to call it this dot compute plane coefficients. Find line from each vertex of polygon J to player. So we want to do an intersection of line and plane. So we have to get our lines now. If this is our polygon J, then we're finding equations for the lines going to each of the vertices of that polygon. So we go through each of our points, we create a vector that goes from the polygon's point to the player's point, which is just x, y, and z here. And then we figure out our t. So we already calculated d, but we have to say this dot d. P4 is this dot xi. But we don't say v3.x, we say v3.0. And that gives us our t value. And then based on these equations up here, we can calculate the intersection point at x, y, z. I'm going to call them ix, iy, and iz for that they intersect x. And after some more replacing, we have our intersect point, as long as I got my math right. Oh, you know what I realized is that I'm using the wrong a, b, and c values for this. You can't compare a polygon's own plane to its own points because they're already intersecting with each other. I don't like the name of the function being compute lines either. I'll call it plane test. We're going to give it an a, b, c, and d value. And then get rid of the thises. Okay, there we go. So now we have our point at ix, iy, iz, and now we have to test and compare it. So hold on. So, okay, now we're going to do idist2. So one of our points is ix, iy, iz, and then the other point is the player at x, y, z. And so we're checking, is the intersection with the plane closer or farther than it is with the player? So we say if idist2 is greater than dist2 I, oh yeah, that's not confusing at all. Right, because if we go back to Newell's algorithm, all vertices of P lie deeper than the plane of Q. And you know what? Actually, I'm not going to make this an if statement because we need to do the check on all of them. And outside the for loop, we're going to say all greater equals true, all lesser equals false. Our new value of all greater is all greater ANDed with our new dist bool. So if it's true, it stays true, but if it's false, then it'll stay false forever. And for all lesser, we do the same thing, but with an or. Well, okay, that's not really all lesser. It's kind of like all not lesser. I guess to make this make more sense, I could say not dist bool, and then AND it with all lesser, and then go up here and make this true as well. Does that make any sense? We're just trying to figure out, like, are all of the points on one side of the plane? So at the end of this, if all greater, then we do one thing, else if all lesser, we do a different thing, and then else, continue with our checks. So all greater should return a 1, all lesser should return a -1. Otherwise, we got points on either side of the plane, and we return a 0. So we're going to say poly j.plane test, and we put in the coefficients of poly I. You know what? Instead of giving it a, b, c, and d, let's just give it poly I. And then we just set the values like this. Okay, and then we have to save the return value into a value. So now what does this actually mean? Hold on. if all the points in the plane that we're giving it are farther away than the polygon that we're testing's vertices, which would mean that if this returns 1, then we draw the polygon of the plane that we're giving it first. So if ptest is greater than 0, now we're doing this within the for loop for poly I, which implies that poly I comes before poly j. And since we're drawing them in reverse order, then we have to do a swap. Then we don't need to run any further tests, which means that we can break out of this loop. Right? And this way I don't have to put another else and then go one level deeper when we do the next check. Because the next check is the same thing except with poly j instead of poly I. And we have to test both because for whatever reason they can be different. I don't really get how it makes sense, but if you just like think about it, it does. But I think if it's the other way around, the swap is probably in the other one. But swapping shouldn't be too bad, right? We just say like quads to draw. We just set one of our values to a temp value. Then within the quads to draw array, we set it to the other one. And then we set the other index to the temp value. And the swap down here is identical. But to prevent it from going into an infinite loop, we only want to swap it once, which means that we need to mark how it's being swapped. And in order to mark how it's being swapped, we need to be able to uniquely identify each polygon, so we need to give each one an ID. So when we create the polygon, we're going to give it quads_to_draw.length as an argument. And the current length of the array will serve as that polygon's ID. And we'll put that argument in here as PID, and then say this.PID equals PID. So I'm making a function up here called swap polys, and I'm just going to pop this into here. And this way we don't duplicate that much code. But now we've got to do the swap add function. So I think instead of using an array, it's probably best to use a map because we'll be able to access things a lot quicker. So let's say this dot swap map is equal to new map. And then down here, this dot swap map dot set poly swap whatever, and we'll set it to true. Let's just do another function in here. So then we just check to see if our map has that value. So it'll return true if it exists and false if it doesn't. You know what, I'm going to call it swap has because that's slightly shorter. Back in render quads, within our first for loop, if we've already done the swap, we don't need to check everything again. So right when we create it, right, we could just say poly I dot swap has poly j. So we'll just break out of that loop, and that will prevent infinite loops. So to soften the blow of it not working, because it obviously won't work, I'm just going to put a break here. That way it'll let me just see the syntax errors first. The first syntax error on line 704, I have a closing parenthesis but no opening parenthesis. Oh, okay, that's it. Only one syntax error. Okay, let me take away the break and put it before the complicated part. dx is not defined. I should be saying this.dx.length. dist2 is not defined. Okay, I mean, nothing even looks different right now. Alright, well, you know what, let me get it down to one pillar. Okay, I think this is the simplest I can probably get it. Oh, you know what, I can make it simpler. I can get rid of the top. So now I just have 4 polygons. Okay, but you know what's interesting now is I can actually track these by their identification number. They're sorted from closest to farthest, and it's putting the dark blue top as the closest. Yeah, no, okay, that makes sense, because what you see is that the dark blue goes on top of the light blue. Okay, so yeah, so I kind of see what the issue is that like it is closer because some points of it are closer. And then what's in the code? What actually makes that switch happen? You get an A, 0, negative 2,500. which is also 0. And we get D. What is D? Negative 227500. Negative 2500y equals negative 227500. Is that a correct thing? Whoa, okay, big plane. Okay, well, we did get a plane. What are our points? 550, 91. Why are they 91? 91 times 2,500. I mean, that's accurate. But why is that like where the plane is? Because that's where the 0 is. That's what we're comparing it against. We're checking to see if this number is greater than 0 or not. This plane is such a monolith. Okay, and now it actually makes sense what's happening, kind of. So because y is always at 91, and they have different planes. The blue one is their z-axis, and the y-axis is the green one. This is our plane. Plane is also, as such, this giant blue thing here. Alright, well, at least it seems like I'm drawing a plane. That's good. So now we do the plane test. So we computed the coefficients of the plane of poly I. Poly I is 2, which is our dark blue top. It is in order 2, 3, 1, 0. And what's our poly j then? Poly j is 2. So we're comparing it against itself right now. That seems, okay, well there's one tiny optimization we can make. Okay, we don't need to compare it against itself. Why does it even swap with the first one anyway? Yeah, I think I have to like reset j when you do a swap. The problem is that not that I reset j, it's that I do a break, but then I have to subtract j, like, because we increase it, so actually, yeah, at that point, before we do the break, we gotta do I minus minus. Now we're checking 1 against 0. Light blue side, light blue top. This would matter if I cared, but I don't. 2, 3. We already did 2, 3. What the what? Why is this false? I hate you. We already did 2 against 3, did we not? There's nothing even in the swap map. Why is there nothing in the swap map? Did we not do the swap? We obviously did the swap. What? Okay, you know what? I think the problem is that this should be a continue, because I'm skipping over the next things, and not a break. So at the current order, it's saying that the dark blue top is closer than the light blue side. This means that it draws the light blue side before it draws the top, which is incorrect. We need to switch these. So wait, hold on. What are we calculating right now? The intersection of the line and the plane. But okay, that's behind us though, is it not? So we're looking at the plane of 2. So at this point, like, we're extending out this plane like all the way out like so, right? And then we're looking at, say, this point. We're checking the intersection. Like, the player's over here, and we're trying to draw a line to this. Like, we would eventually hit the plane if it's like down there over that way, but that's in a different direction than the shape is. But then it would still think like the distance is like over here, and it would still like think about like, oh, this distance to the point over here, and then it would think to draw this one first because it's closer. So I don't think I accounted for that. The problem right now is just like, it's so hard for me to envision where these points even are. Okay, so I went and graphed everything. So again, the green line is the y direction and the blue line is the z direction. So it doesn't exactly match, but the principles remain the same. You can see the plane of poly I. B is meant to be the player. A is one of the points of poly J. And then C is, if you draw a line from B to A, that's where the intersection is with the plane. But then after that, what it would do is it would check the distance between B and C and B and A, and if B and C is shorter, then that means it's closer. But C is behind B and not in between B and A. So really there is no conflict. And I didn't account for the line going backwards as well as forwards. Luckily, that's very easy to figure out in the code, because if you just type in t, you can see our t value right now is negative. And if t is negative, I write, because I think at 0 it should be equal to the point we're at. Is that correct? Let me check that. So x is 400, y is 0, z is 300. So we should, if we plug 0t into the equation, we should get 400. Shoot, get the initial point. Should we be graphing this from, it would probably be better to graph it from the other way around, wouldn't it? That way the 0 point is the player, and then whether t is positive or negative gives us the direction. I mean, I could just swap these, couldn't I? And that way the 0 point is at x, y, z. So we're just gonna swap this around. D minus a, so instead of this dot xi, we just change it to x. So now we're using the player instead of the point as our initial point. And then this is the same because this is the vector, and then we just swap these around, right? And then that should be the intersection point. And if t is positive, then that tells us, okay, so let me check that. Okay, since t was negative, I think perhaps the vector was pointing the wrong way. So I switched this dot x and so on back around, and that gives us a negative t vector. I guess if t is less than 0, we just continue, maybe. That might work. D is the next point, and D, actually this time, it crosses the plane. So this time it's actually in the right direction. So that's good. It should be positive. All right. No, wait, what? This is saying D is behind the plane, isn't it? What? Right, I calculated the plane, but the plane is just at 91, and that's what it should be. And the point D is at 100. So then it's intersecting with it, is it not? In the code, I calculate these things and draw them. How am I doing it? Yeah, so our side face here is digging down into our top face about 9 pixels, because I did math wrong. So we want to make it flush with it, and the fact that it's digging down into it is causing a problem. Newell's algorithm would cut these up at the intersection point, but I don't feel like doing that yet. So therefore I need to actually construct my polygons correctly. And here's the culprit right here. This is our height, and I'm just subtracting prop ends, which is our proportion of the endpoint, but because it's at the bottom, it needs to be prop ends times 2. Let me just go through this again then. We end up with a t of 1. I think I could just say if t is equal to 1. Let's just try this first. And so the reason why I want to ignore where t is equal to 1 is because it's on the plane. So you won't know whether it's on either side in that case. Okay, let's try this again. Okay, that looks correct. And it looks correct on the other side as well. Oh, okay, yeah, that's okay. It's not working. So yeah, it works for this, but clearly some other math is going wrong. So this still looks fine. Oh wait, hold up, there's something weird there. For like a second, it goes weird. And then when I uncomment everything, then it starts looking a lot more weird. Okay, there's an error. That's interesting. So I wouldn't debug this slightly more now, and it really is seeming like a precision error. The point is that when we look at the point, right, you see it's on the plane pretty much. And we have a slightly different plane. Now our plane's at 100 instead of 91. And here we're getting 100.000001. So it's just slightly off in its precision, but the problem is happening in the intersection point at the Y position. We have 358.5743. And if we dist between points, IX, IY, IZ, X, Y, Z. Oh, wait a minute. That's significantly greater. Why is that significantly greater? So we're trying to go from there to J. And you'll see that what is supposed to be the intersection point here, it's not on the line. You know what? I think I found the issue. Yeah, so the only reason we're breaking here is because we have to restart because we swapped the polys. Right? So we're still continuing to do the loop. Up here, though, I'm breaking, and I'm not decrementing I, so I'm not doing the thing again. So this probably shouldn't be a break, but a continue. I wonder if that fixes the problem. Let's see. And it did. Look at that. Beautiful. No. No, we're still getting some artifacts. There's less of them, and they only happen sometime. But you can see it happening, like, immediately. But it doesn't happen here. That's interesting. It's only when the top one's there. That is so weird. But look at that! That's so weird! Look at that! It works! It's only when there's one to the left of it. Okay, now that's super weird to me. Why is where I look changing it again? That shouldn't be happening. That seems like another swap error type deal. Because when I turn this way, once those blocks are behind me, then it jumps in. So what changes in my view is the number of polygons that are on screen. So that means it's a swap problem. You know what? I think I figured out what's happening. I don't know how to fix it yet, but I know what's happening. So let's say this is our sort list, 0, 1, 2, and we want to get in the reverse order. So 2, 1, 0. The way that our swap algorithm is working right now is kind of terrible because it's bubble sort and it's also a non-working bubble sort. So let me just work through it. So we'd start with 0 and we'd look at 1 and we'd say, okay, well, let's swap these around like that. And then we mark that we did that swap. So we'd say 0, 1 over here. And then we'd look at 1 and we'd see 2. And we'd go, okay, well, we have to swap these because they're not in the right order. And then again, we'd mark that. So we'd go 1, 2. Right? And then it would look at 2 and it'd see 2 is fine. And then it would look at 0 and it would say, okay, well, let's swap 0 with 1. Except it then goes and checks the already swapped and it says that that's already been swapped. And so it just won't swap it. And that's basically what's going wrong. The reason why this already swapped thing is a thing is to prevent things like cyclic dependencies. So that way we can't just go back and forth between the same two polygons. All right, so here's my alternate way of sorting that will actually end up with things being sorted. So we do the same thing as before, where we have 0 and 1 and we swap them. And as such, we go and we mark that we swapped them. Now we get to 1, and 1 and 0 are sorted, so that's fine. We get to 1 and 2. So now we're going to pull out 2, and we're going to put it where 1 is. But when 1 goes to try to swap with 2, it's going to go and look up at its sorted, and it's going to say, well, actually, it'll know the position of 0, and it'll know that it can't go any farther than that. So it'll go and put 0 in its spot, and then 1 will go in 0's spot. So now we get to 2, and we want to swap 2 and 3. Okay, and same sort of deal, right? We can move 3 over here, right? But 2 is going to go, and it's going to look up, and it's going to say, well, actually, I already swapped 1 and 2, right? And so it's going to go and try to put 1 in 3's position. But 1, before doing that, it's going to check and it's go, well, actually, I already swapped with 0. So it's going to go and put 0 in that position, and then 1 will go in 2's position, and then 2 will be able to go in 1's position, and so on like that. And then it ends up being sorted, while we still like don't swap anything more than once. We're not going to need swap map anymore because we have to check everything. We can't just check one thing when we do a swap at this point. So instead we're going to have a this.swap array. So that means when we do an add, we just push the new polygon onto our array. What we also need though is, besides the fact that there's a PID, we also need the current index, which we're going to have to keep track of. Actually, you know what? I think I decided is, instead of having swap R, we're going to have two different swap arrays. So we're going to have this dot swap before and this dot swap after. We're going to add before, and we're going to duplicate this and add an add after. And the reasoning behind this is that it'll be a little bit more optimal to not look through everything, because we know which direction we're swapping in. Why should we check both directions, kind of? The first one goes to the right, so I think that's an after, and then the other one is before. I'm just going to comment this out for a second. So I think first we have to iterate through poly I. The I and j here aren't really necessary anymore because the poly I should have their cur index. So whatever, get rid of those. I equals 0, while I is less than swap after. Okay, no, actually we look at the before, it looks like, dot length, and then we iterate through that. This is our swap max, I guess. Is that kind of what it is? And then poly j would be something that we would look at. We'd get its cur index. It's the index we're swapping with. You know, it's just like idx swap and idx max. Basically, the idea is that we can't go any farther right than that. So we have to compare against it. So let's say we're trying to swap 4 with 1. And we've already previously swapped with 9. And you can see here 9 is in between the two. So we'd look at 4, and we'd go into our swap, and we'd look at 9. And then we see that 9's index is 2. And then we'd also look at 1, or we wouldn't look at 1 so much as we'd look at the index, and we'd say that's 3. We'd say 4 is not allowed to be at a position greater than 2. So it would do the comparison here. Is 2 greater than 3? Yeah, right. And if it is, then we have to swap 9. So what is that? That's our IDX max over there. So we have to swap that. If IDX max is greater than IDX swap, then, I don't know, do another swap. Okay, so then we want to do this recursively. But you know what? I want to do this in another function, right? Because we have an inner part and an outer part of this function. And the inner part is what we do recursively. So poly I.swap before I, that needs to be a new poly. Swapper poly, that's kind of long. I just call it sPoly. You can go sPoly.curIDX, the swap poly, and poly j. What we're going to do is we're actually just going to move this whole thing out into here. And then when this starts, we call swap polys inner. Oh man, now I have a recursive for loop and a for loop. We haven't actually swapped anything yet, right? Yeah, let's say else. Then we do the actual swapping. Yeah, polyj.curIDX equals poly I equals poly j. Yeah, poly I.curIDX. And okay, so now we swapped the indices, we've swapped the polygons, and actually the one other thing that I care about, I only want to add to the swap list if it's actually like done on a comparison. So I do that outside of the inner part. The question is, okay, what if there's nothing in the previously swapped array? You're just not going to swap anything? So, okay, alright, I think it needs to be outside the for loop. Did I get this going the wrong way? Can I do it the other way? Is that all? Is that all I have to do? Okay, what do we got? Poly_i.swap_has is not a function. That's an optimization, isn't it? Alright, let's just comment it out. This is all the same thing. Loading. Oh boy. That to me suggests infinite loop. What does the swap before look like? It's empty. Yes, swap add before is right here. Oh, okay. Alright, I see. We have 11,950,287 polygons in our swap before. That seems wrong. You know what the problem actually is that the purple number here, which is the index and the quads to draw array, is not matching up with the current IDX because of this original sort function. So I guess after we sort everything, we have to set the cur IDX of each of them. So cur IDX equals I. And that should fix it. It looks like it's just now going back and forth between 10 and 25. At least they know they're in the right spot. Does poly_i's swap before look like? Is it all the same polygon? Yep. Okay, so I feel like I'm so close here. And I'll cover exactly the changes what I did when I go back and figure out what's necessary and what isn't. But like, look at this. Look, it almost looks perfect. But then you go real close and it breaks. And that's because of this. That because the darker polygon is wider, those points end up being farther away than the lighter lines. So instead what we need is we need to find the distance to the plane. Or to explain using 3D shapes, imagine this square is our polygon, and this sphere represents the minimum distance of the closest vertex. And you'll notice that if we drag the polygon over to the sphere, all of the four corners can be touching, but the center of the polygon is actually closer. Right, the center of the polygon is flat, so it's inscribed inside of the sphere. And we can just add it to whatever point, because all the points are equidistant anyway. And that's the bounds for our min distance. And here's what I've come up with. So this is a two-dimensional model of what's happening. PQ would represent this dark blue that's going closer than it should be, essentially. In this model, we think that it's following this arc line here, because that's what the math is saying, but it's really going straight from P to Q. And so this isn't all of cases, because the polygon can be angled in different ways, but in a worst case scenario where P and Q are both equidistant from each other in opposite directions, then we have to sort of assume a lower bound for how much the polygon is popping out, which would be most at the midpoint here. So first, calculating the angle theta isn't too hard. It's just 180 degrees minus this angle of PCQ right here, divided by 2. And then from there, D is equal to R times 1 minus sine theta. So we do sine because opposite over hypotenuse. Right, in the unit circle, that would be 1. And then once we get this distance here, we do 1 minus it to get the other side, which is D. And then I guess we multiply by R to scale it up. So great, now that we have D, we've got the worst case, the lower bound for how far it could be popping out. And the way that we figure out where P and Q should be is by this, I think. This should maybe work. The field of view multiplied by, I guess, the bounds of that rectangle, which I'm saying is dx and dy. And then we take the
hypotenuse of that to get the maximum distance. So then kind of once we have this diagonal line here, we divide it by the screen width, because I think field of view is calculated by screen width. And that gives us a proportion of the field of view that it's taking up, which gives us this angle here. And then of course we are able to do this and then this. From there, we're just going to subtract off this distance from the min distance of whatever our point is. So let's see, this dot min dx plus, well, the distance, right? So we do this dot max dx minus this dot min dx. We square that, math.pow. We add that to math.pow. This dot max dy minus this dot min dy. Square that. Then take the square root of that. And then this would be the display diagonal. We have the display diagonal, which is this. We divide it by screen width. So the display diagonal divided by canvas.width. And then we multiply this by field of view. That gives us the proportion of the screen that is being taken up by this diagonal. And this is, what are we going to call this? So I could call this PCQ. Is that what I wrote down here? So I guess R is the minimum distance to one of these points. So I think I call that mindist, this dot mindist. We multiply this by 1 minus sine of theta. I don't know, like a projection displacement. That is a no. I mean, it's kind of like a spear shortcut. Sphere cut. Okay, hold on. I gotta pop in. Proj warp. No, but it's not. That's not what's happening. Decent name here. Poly incut. Poly incut. Ah, yes, the incut of the poly. Everyone knows what that means. Chord distance from edge of circle. Oh, it does have a name. It's called the sagitta. What a great name. We're gonna call it the sagitta. Oh yeah, I didn't put theta in. Degrees to rad, math.sign. Yeah, so we have to do something with the sagitta. Yeah, I guess we would say this dot mindist minus equals sagitta, like that. So I'm just gonna get rid of this whole calc extents thing. Now our mindist is gonna have the sagitta. I swear I'm probably pronouncing that wrong. How do you pronounce sagitta?
Sagitta.
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 Sagitta. Why is this video so long? Did that fix my problem?
You know what I think I forgot to do? And I think the reason is because in swap polys, I'm setting the must be before and must be after in there whenever I swap them. But if I don't swap them yet still come back with a conclusive test, I'm not doing that, right? So all this stuff, swap add after, swap add before, swap add, right? I could make this its own function. I don't know, I'll just call it swap manage. Grab all this stuff, put it here, call it swap manage. Then also put that here as well as here. So actually, maybe the problem is that I did it in the wrong order, that I need two different situations here. I don't know, after first, like if after first. Otherwise, we do it in the other way, for first. I didn't think that hard about this. This might not work. So this is false. This is false. And then within swap polys, we make it true. Work for me, work, come on. What is, no, come on, don't do this to me. Okay, it maybe seems a little better, but we're still getting some bugs. Oh boy, now I hit a big snag. So I've labeled these polygons here because this is what their polygon IDs are, but this is kind of irrelevant. But basically, what's happening is that we have a polygon cycle. We're saying that 2, right? So this is polygon 2 right here. It's saying 2 should be closer than 10, which is correct. Then it's saying that 10 should be closer than 11, which it's kind of ambiguous because 10 is this polygon and 11 is this polygon, so it doesn't really matter. And then it's saying that 11 should be closer than 2, which is kind of right because if you extended this upward, then that would be the case. But then this ends up being like cyclic polygons. I have some code that's preventing an infinite loop, but as a result, it does kind of lag a little bit. And then not only that, but it doesn't work. So I think I have to go and implement the part of Newell's algorithm that I didn't want to implement, which is rasterization and splitting of polygons. Which means I need to figure out how to tell if two polygons are colliding. Okay, screw this. This is a let's play now. Push button to disarm bomb. Okay.
The Mega Scuttler is now armed and preparing to explode. This will be a fairly big explosion, so please stand back about 22 miles. 995.
What is this thing?
994.
What do I do with this?
That looks like Titania's vision center.
Again, what does that mean?
That looks like Titania's vision center.
And I guess we can record music. I don't know what's happening. Okay, good music. I don't know any of this means.
898.
That's it? You only got 100
897.
seconds?
Recommencing countdown. 1,000. 888.
Okay. So now I'm in a robot art gallery. Well, I don't think any of this is doing anything. This is more contemporary, or less contemporary. Whoa, what the frick? I think I did something. This. That. Other. What does any of this mean? You're supposed to make any progress. You're just supposed to just...
802.
You're only on 802? Can you just blow up already? I want to know what happens when you blow
800.
up.
Oh, I think that got lost. You'll have to see Mother.
Who's Mother? What does that even mean? Where are my items that are lost? Can you tell me that?
Over there.
You are very useful. What does this button do?
Bilge room. Going down.
Oh, shoot! This is Mother.
Oh, I don't feel well.
What are you doing? Can I put the feather in here? Where are my items? I lost my feather.
Get out of it.
Bomb ticking away nicely as it's up. I was speaking metaphorically as it happens. That sort of thing is down to successful intellectuals like yourself, sir.
Oh, cool. A chicken. Do you want the chicken?
Ah, chicken. I love chicken.
Why? For what purpose? What did that do? Why is... What? What? What is this? What is this? Oh, I can smash the glass. Yes! Now I have a stick.
509. 508. 507. 506. 973,762,031,616 combinations to try. So it's either that or get a life. 471. 470.
I don't know.
469. 6, 5, 4, 3, 3 and 1. Look, I'm a bomb, for heaven's sake. I'm bending over backwards to be fair and reasonable, but at the end of the day, I'm a bomb. And what bombs do, not to put too fine a point of it, is They blow up. Recommencing countdown. Now, 1,999.
Did he just literally restart?
709.
Are you freaking kidding me? Okay, you know what? Never mind. I think actually coding a 3D engine might be easier than this game. Okay, this is maybe not that bad. It did take a while to figure out exactly what they're talking about and how to apply it to my situation.
Our goal is to figure out if these two polygons are colliding. And to figure that out, you can use something called the separating axis theorem, which states that if two polygons are not intersecting, then you can draw a line in between them. And there are many possible lines that you can draw usually, but also at least one of the lines is going to be on at least one of the polygon's edges. And if we go and find that line, and then draw a line that's perpendicular to it, we can look at each of the points of each of the polygons and go and project them downward using dot product onto the perpendicular line, and then we can go and do a simple greater than less than comparison to see if one of our points of one of the polygons lies within the range of one of the others.
Yeah, let's try to actually write this function. So I don't know, I'll just put it in this space. Polys intersect. Yeah, so let's just comment out this section here and paste this in so I know what I'm doing. For all lines on poly P, let's just call it iPolys because, you know, for intersecting polys. And then let's do poly P, poly Q. Okay, no, actually, I want it to be poly I, poly J going in. And then we could say poly P equals iPolys I. I'm going to call this vector lil perp because it's perpendicular. Y minus poly P dot P plus 1. Yeah, I don't feel like typing poly p.dx.length every time. That's just annoying. All right, yeah, PPL. So mod PPL. What am I writing? I forget already. Okay, comma. Oh right, we have to make this an array. The second part of set array is pretty similar, so we're just gonna copy this, but then switch the order around. And that's our perp line. That's our perpendicular line. So the magnitude is lil perp 0 squared plus lil perp 1 squared. But then math.square root normie vec lil perp 0 divided by magnitude, comma, lil perp 1 divided by magnitude. Yeah, there we go. So if I wanted to, right, I could say lil perp.map. I've never used this function before. Why am I using it? Let me test this just because I've never used this before. X, whatever, arrow, x divided by 5. Ooh, it works! Okay, I'll just assume that it functions. That's a cool func. I should use that more. So, more for loops, ew. Alright, j is less than 2, j plus plus. Okay, hold on. While q is less than CPL, q plus plus. So, proj points of j dot push. So yeah, normback 1. So this is check poly dot dxq, and over here this is check poly dot dyq. Wait, didn't I have to do dot product? This is not dot product. Yeah, I think this needs to be a plus here because dot product gives us a scalar value. So same deal. Make it a scalar value. Okay, find min and max of projected points. Instead of proj points, we're going to have polymin and polymax. Yeah, so then we say polymin of j is equal to math.min of polymin.j, and our proj point. Do the same thing for max.
And then we need to initialize this. Yeah, so negative infinity, infinity. This is like what? Like polymin 0, polymin 1. You know what? I think we should be declaring not overlapping outside of this. So if true, break. Okay, I don't like that. I don't like that. I don't want to break if true. No, overlapping is true. They are overlapping, yeah. And then just put a big knot at the front, yeah. So yeah, okay, and we're gonna say and overlapping. So that way it breaks out of the loop, and overlapping. So if we ever see that they're not overlapping, then this is false. So it stops evaluating it. Then overlapping also this is false, so we stop evaluating. So if overlapping is true, then they intersect. Yeah, so return overlapping. If we ever break out of the loop, that's because we found a line that separates the two. And once we found a line that separates the two, we know that they can't be intersecting, so we return false. Now, how do I test this? I feel like I need to put this in its own test program.
Right, so here's my test program. Got 2 polygons defined here. The polygon class is a lot smaller. We draw them here, check if they intersect here. And then here's the polys intersect function. I mean, there's other stuff, but who cares? Unsurprisingly, it doesn't work. But what I realized I'm doing wrong is when I take the min and max, I'm doing it wrong. So we want positive infinity and then negative infinity for the max. And polys don't intersect. Oh, it knows now. They still don't intersect. Ooh, oh, it actually worked. That's surprising. I believe the method that I looked up online actually functions. Polys intersect. Yeah, polys don't. Oh, I mean, it seems like it's working. So let me go and copy the function back. So now that I have a polys intersection function, okay, basically this is a measure to prevent loop swaps more than once. But if you have a cyclic loop, which is what we're having, I'm just saying if the same swap comes up again, go back up the stack. But somehow instead of doing that, what I want to do is check to see if these 2 polygons are intersecting. And if they are, we could try and eliminate a restriction that they can't swap. So now it's mostly working, except the screen goes blank when it infinitely loops. But most of the time it works otherwise, right? There's an interesting way where we could fix this, right? Where we could just not draw the screen and it would maybe be a little stuttery. Yeah, so there, oh yeah, there, yeah. That's about right, I think. That looks good. Now, what I meant to do was drag the refresh after we do the render quad so that if it fails, right, it won't update the screen, right? And then, you know, I mean, it's a little stuttery, and by a little, I mean a lot. Yeah, look, it's, yeah, just a little bit stuttery, but it's almost playable. Wow, this looks terrible. Okay, so this is not feasible, let's be real. Okay, and miraculously, I think I finally got this working, which is great. And wait a minute. Oh, come on. Are you kidding me? Why do you do this to me? Why is it not functioning? Okay, all right. Right, so dark green should be on top of light green, meaning 1 should be before 0 in the sort list. So what's actually happening? So for whatever reason, our plain test is coming back with a positive value, which means we swap. You know what may be the problem is that maybe t is like between 0.99 and 1.01. Yep. So this whole t is greater than and less than thing, that was a dumb idea. I guess the bounds of this are too large. I'm just gonna say equal to 1. Right, okay, and that's why when you get closer, it was fixing itself, because you're closer, so the proportion becomes less. And we're back to normal, and we don't have that issue. So we're drawing them correctly now. Fantastic. Okay, so it's like it miraculously works now. Mostly. I mean, there's going to be some issues. I think if you get like up real close, yeah, see, like it's peeking through there, and like what's the deal with that, right? But that's only if you're like super close to this thing. I feel like my head is actually like poking through the polygon, and that's kind of why that's happening. If there was collision here, you wouldn't be able to get that close. Okay, well, it's not perfect. Look at the light blue pillar on the right side there. I think it just hates me. But anyway, let's do a code walk because I was too busy pulling my hair out to try and actually explain any of this as I was doing it. But I'm going to first cut the number of pillars down just so that it doesn't take as long to get through things. All right, let's go look and see what's happening. Right click, inspect. And I go and click in the game loop and paint screen. Quads to draw is a list of all the polygons that we're going to draw to the screen. And on line 608 here, we are emptying the whole array by setting it to a new one. Here we're setting the canvas's color to green, and then we're filling in a rectangle the size of the screen with that color. So that's why the screen is green in the background. Then we're setting our style to black, though we don't use that, so that line's kind of unnecessary. And now we're iterating through all of the different rows of pillars. In this case, there's only one row of pillars because I intentionally made it one. This line here is some wacky modular mumbo jumbo to make it so all the pillars are different colors without me having to actually specify explicitly what color is which. And then we're drawing the pillar, and you know, this was covered in the last video, but let's go into this function anyway. We're defining the proportion, which is the top of the column, and the proportion of how much the pillar goes inward. And then we're creating the center of the pillar here, and we do that by drawing 3D quads. I don't feel like going into each of these. And okay, you know what, let me go into one of them. We draw the prisms by drawing 6 3D quads. And then within each quad, we get the 3D points by doing like math and stuff. If we determine that at least one of the points is in front of us, then we decide to actually go and draw it. And instead of actually drawing it, we just decide to make a new polygon, right? And here's the polygon initializer. We just basically initialize some values, calculate the distance to each point, and figure out the min and max of each value, as well as the min and max of the display values being where we're going to draw on the screen as opposed to where they are in 3D space. We calculate the sagitta, which is how much the polygon could be at most coming out of the screen. That way we don't not consider the polygon in the sorting phase. Defining the functions. And then instead of immediately drawing the poly, we push it to an array to go and sort it. And then the last thing we do in the paint screen function is we render the quads. So now we're in the render quads function. So the first thing we do is we sort the polygons by their distance from the player, from closest to farthest. But this is imperfect because we're not considering every point on every polygon, we're just considering the vertices. So now we have to do a bunch of swapping to fix it to actually put it in the right order. We go and we iterate through every polygon and we assign it its index within the array because otherwise it wouldn't know where it is in the array, and it needs to know that for the swap phase. We can look at the quads to draw and we can see that it's 18 polygons, and we can see the order and the way that it looks right now. But now we begin the swap phase. So we're going to go through every polygon and we start comparing it with the polygon that's right in front of it. So if we look in the watch, we can see that we're comparing polygon with poly ID 1 against poly ID 2. Now this line is checking to make sure that we haven't already swapped before. If we've already swapped these two polygons, there's no reason to do it again. This line checks the z distance. Are these two polygons even within the same z distance? Is at least one vertex within another one's vertex? Basically, if we reach the point where the next polygon's closest vertex is farther away than our farthest vertex, then we know that it should be sorted at this point, and we can actually just straight up move on to the next polygon and just consider polygon I to be sorted. So the other part of this if the else here, is a break statement. So we break out of that second for loop and move on with the first for loop to go on to the next polygon. Now this next line is a rectangle bounds checking. So it's very easy to draw a bounding rectangle around each polygon. And if these bounding rectangles don't overlap, then we don't need to compare them at all. But if they do overlap, as in this case, even though these two polygons aren't actually overlapping, their bounds are, so we have to proceed to check them. Because actually checking if the polygons overlap is a bit more involved. So at this point, what we're going to do is we're going to find the plane of polygon I and check if all the points of J are on either one side of the plane or the other. So within the computed plane function of the polygon, we have this computed plane boolean just to make sure that we don't do this more than once, because once we do it once, it doesn't matter. I mean, we probably could have just done this on the start of the polygon. It would have been just as efficient anyway, so it doesn't really matter that much. But in here, we take the cross product of two vectors to find the A, B, C, D coefficients of the plane equation, which we will use later in the plane test. And oh, look at that, we're in the plane test. So we take the coefficients of poly I, and then for each vertex of J, we find the vector line, which is V3, and we find the intersection of the plane by finding T, which is a parametric variable. So if we plug T into the linear equation for X, Y, and Z, which is what we're going to do down below, we figure out the X, Y, and Z point of the intersection point of the line and the plane. Now the reason why we're checking to see if T is less than 0 or T is equal to 1 is because if T is less than 0, then that means that the intersection point with the plane is behind us, which means these polygons don't overlap. And if T is equal to 1, this means that the two polygons are the exact same distance away from each other, so we can't use that to tell if it's closer one way or the other. So we go and we find the intersection point, and at this point we calculate distance between the intersection point. To be more clear on exactly what that intersection point is, it's the distance from the player's location to one of the points on poly J that passes through the plane of poly I. And we're checking to see if the intersection point with the plane of I is closer to the player than it is to the point of J, or it could be over here, and then J would be closer to the player than the intersection point. And so that's why we're finding the distance, and we're doing the comparison, and then we check this for all points. In this case, all greater is false. All lesser is true, though. So we're returning a definitive value. All of the points are lesser, whatever that means. And as a result, that means that I is closer than J in this case, and we want to preserve that. So we have this swap manage function, and so on poly I, we use the add before to poly J, which if we bump into that function, we see what we're doing is we're taking the polygon here and we're saying that whenever we're doing more sorting, I has always got to be before J in the list. We're doing that for J too. We push poly I onto J and we say J must always be after poly I. We have this swap add function, and this is setting the other polygon into its swap map, so it knows never to try and swap these two again. So we keep poly I the same, and we move on to the next poly J in the list, which is 12, right? So we haven't done 12. We check it, do the plane test with 12. In this case, though, the plane test wasn't conclusive, meaning some of those points were on one side of the plane, and some of the points were on the other side of the plane. So now we're going to do the same thing, except with J instead of I as the plane. And the result of that is that we should just keep everything the same again. The next poly, we're comparing 1 against 13 now. Okay, this time we find that we want to swap the polygons. So let's go in the swap polys function. So, unsurprisingly, you might expect that swap poly swaps these two polygons. But it's the swap poly's inner that actually does the swapping because it's a recursive function. So let's jump into swap poly's inner, see what that does. So the first thing that we do is we create a tswap string, which looks like 1 swaps with 13, which is basically pretty similar to the has swap that we had before. This will prevent loops and that kind of thing so that we only do each swap operation once. But the difference here is that the tried swapping is only active for the given swap, and after it's done, we clear it. So here we're checking, have we done the tried swap for this specific thing before, or are these two IDs equal to each other? Are we trying to swap something with itself? Since neither of those are true, we add the tswap string to the tried swapping map, and now we're going to check the must be before arrays and the must be after arrays for the I polygon. So first we check must be before. Remember, that means that that polygon has to be before whatever is in the must be before array. We're trying to swap poly 1 with poly 13, and in poly 1's must be before array, it has poly 2. We look and we see that poly 2 is in index 1 of the quads to draw array, and poly 13 is at position 3. Since must be before swaps rightward, we check to see if poly 13, which is the swap, is greater than the maximum position that is possible to swap, which is poly 2's 1, because we know that it's got to be before that. And so what we determined in this case is that poly 2 is in between poly 1 and 13. So we can't just swap them because things would be in the wrong order. So first we have to swap 2 and 13, which is what we do recursively by calling swap polys inner again with our new poly. So we go back in, we do 2 and 13 this time. We check 2's must be befores. We don't find anything. We check 2's must be afters. We also don't find anything. So that means that it's okay to swap. So we go and put 2 where 13 is and 13 where 2 is. And we also change their stored indices within their own polygons. And then we go back. We return true, saying that we did swap. And I'm going to call quads to draw again just to see how that updated. And you can see in the quads to draw array in the console here that 13 and 2 have swapped, but 1 has another must be before as part of it, right? It's must be before 12. Well, now that we've done the swap, 13 actually is before 12, so there's no conflict here. So we leave, we check the must be afters, but it doesn't have any must be afters, and now we're good to swap 1 and 13, which is what we do, and we return true. And now we head back out of the swap polys function because we swapped all the polys, and we can look and see what the quads to draw array looks like at this point. And you can see that the order now goes 13, 1, 12, 2. We clear our tried swapping array. This stuff here is some stuff that we would do if things were false, but since we return true, we just go into the swap manage down here. We add the swap befores and afters, and we say that we've done the swap. So now we're outside of the swap polys function at this point, but now we have a new polygon, polygon 13, at the front of the array. So we can't really be checking 1 anymore because 13 is first now. So we go and subtract 1 from I simply because when we go and break the loop, it'll move on to the next poly I. So when it does the plus plus operation, it'll be in the same spot. And since we are in spot 0, we'll still be at index 0, but instead of the 1 being there, we have 13 there. And so now we check 13 against 1. But we just did 13, 1, so we're not going to check that one. So now we're doing 13, 12. Does anything interesting happen in 13, 12? Nothing interesting happens. 13, 14 isn't particularly interesting. Okay, so now I've skipped ahead a bit. At this point, we're trying to swap 7 and 10. 7 is in the first index and 10 in the third, but 1 is in between them. And 1 said that it's got to be before 10. So this is a conflict because 7's got to be before 1, and 1's got to be before 10, but 10 has to be before 7. So we end up in a loop, which means that we end up trying to switch 10 with 10. Inefficiently here, I guess we're trying to check to see if polygon 10 intersects with polygon 10, which of course it does. It's the same polygon. But whatever the case, it returns false for that reason, meaning that the swap was unsuccessful. So we're back a step. We're in a 110 swap, and since the return value of its swap polys inner is false, it goes forward a bit, and now it wants to check to see, hey, if you were to draw polygons 1 and 10 on the actual screen, would they intersect? Should we actually care about the order of these two polygons? So let's go into the poly intersection function. So we know how this works then. It checks to see if it can find a line that separates the two polygons, and if it can find said line, then that means that they must not be intersecting. But apparently they are intersecting, so we return false. So now we're back at the 710, and so we do it the same thing with it. Do polygons 7 and 10 intersect? Okay, apparently they do. So we just leave and we just say that it's fine. Okay. Had things gone another way and we found that poly I and poly j did not intersect, what we can do is we can unset their must be before and must be after arrays so that we get rid of those requirements. So we pop into here, we search through the array for whatever polygon it was that we were swapping with, and we go and we splice the array, which removes an element. And then we go and return the swap string. And for the most part, false and returning which elements we swapped mostly works the same, but the reason why it's there is so that if we go back out of the loop, which is here in the outer part of the function, we'll see we've returned 3 and 14. And had the return string been different than the one that we're trying to swap with, that would mean that 3 and 14 are still required to swap. And so if we were in this inner if loop, and that didn't happen in this case, we would try swapping again because something changed in there. But we only do it once because that's to prevent infinite loops. And since we didn't return true, we don't want to go and save the swap values because nothing swaps, so we don't want to enforce it. But we do want to add that we did in fact do the swaps because we know that they don't intersect, so there's no reason to ever try swapping them again. Yeah, that's basically everything. I have all this code here. I'm just going to put it all the way at the bottom of the file here because I'm not using it and there's no reason to just leave it in there because it's not affecting anything. And yeah, it would go right in here and you'd get rid of the continue, which I can do now. And it should work exactly the same otherwise though, which it does. Next time, I'm going to break this because there's plenty of stuff that don't work. And oh my god, are you freaking kidding me? I just saw something not working. That was... Look at that. Look. Okay. What the... And I'm pretty sure I could get this to break if I just put a diagonal polygon that went at a diagonal to one of these pillars, which is what I'm going to do next time. And I'm going to scream trying to fix that. Though maybe you could split the polygons to fix that, but even splitting just seems really annoying. I mean, splitting is what's actually part of the algorithm. Oh, but you know what's actually, more fun than this? I liked getting rid of the clear screen line. Where was that? Yeah, I mean, who cares about, like, this whole, like, yeah, like, this looks great. This is what I'm talking about. This is, like, going out of bounds in Doom 1. Whoa, you see that? You go in a polygon, it changes the background color, and it also clears everything. Oh, that's sick. Oh, it's like I'm data moshing. What if I, like, look down? What does that look like? Oh, yo. What? Oh, yo, you look up and you turn in a circle? I can't figure out where I am right now. Look up, right? Look up? Yeah. Oh, wait, yo. Oh, it's like I'm playing Manifold Garden. Oh, that's sick. Oh, look at that. Oh, now it's really like I'm playing Manifold Garden. It's like I'm in the land of infinite pillars. I really like this image. Wait, hold on. I bet I could get like See, the thing is, the YouTube thumbnail's small, so you have to like really think about what you're doing.